Okay, I'm Quinn Jacobsen from Achronix, and we just had a great presentation on SmartNICs. I'm going to dig a little bit more from the hardware perspective of the SmartNICs and about what we're thinking of prototyping. I'm concerned this has been a very quiet audience. I'm hoping you guys are going to wake up here after the break and maybe a little bit more coffee. So we've talked about SmartNICs, and given the presentation before, I'll go real quick on what they are, but you know, it's a NIC that offloads work that would otherwise have to be performed by the host system. And this is a problem that's becoming more and more important in our data centers today. And we think it's a good candidate for a proof of concept for something like the open domain specific architecture, because it's an area where everyone wants domain specific accelerators for SmartNICs. And all the building blocks are common. Everyone knows what it looks like, but then everyone has their own requirements and has slightly different architectural features they would like to see. So that's why we think this is a good demonstrator of the power that chiplets and these more composable architectures can enable. So if we take it at a very, very high level from a hardware perspective, what does a SmartNIC look like? Well, it's going to have some Ethernet ports. So it's going to have a couple of QSFP cages. It's going to have a PCIe connection to the host. And it's going to put a lot of traffic through that. And if you're wanting your SmartNIC, what do we want on them? Well, we have this really long list of requirements that we want them to be small, fast, cheap, and very flexible. So if we dive in a little bit more, the heart of this is a programmable engine that can basically take these incoming traffic, match it, and perform a set of checks and processing of the traffic. We need this to be flexible because people are wanting to update the protocols and the acceleration. But they also have to be very low latency and high throughput, because as we go to faster and faster connections in the data center, we need to be able to push more data through the NIC. And as I said, there's constantly changing requirements from security and from an acceleration perspective of capabilities we want this to handle. And so we need to make this a programmable engine, and there are lots of ways we can do that. So I'm going to talk a bit about some of the options of what are the building blocks of how we build a SmartNIC. So to process all these packets, there's really a range of options we have. So we have custom data path, where it's clearly the most power and area efficient. And it can easily handle, say, a 400 gig Ethernet connection. But you have to figure out all the configurations you're going to ever want ahead of time before you build it. So as long as you plan for it and make it a configuration parameter in the system, then you can handle it. But if something changes and that's on your performance critical path, then you have a problem, and then you'll not be able to handle that capability in the future. We have CPUs, and we can do lots of CPUs, be they RISC-V or MIPS or ARM, whatever CPU you want. They're very flexible. Everyone knows how to program them. They're very easy to update as things change in your requirements. But there's also some performance limitations of how CPUs can efficiently handle this ever-growing bandwidth feed that is coming into a NIC. FPGAs are another approach to how to address this. A reconfigurable data path that's composed of lookup tables and configurable routing fabric. They're not as power efficient or area efficient as a ASIC, but they're also reconfigurable. So as long as you have capacity in your FPGA, you can fundamentally change the data path and the algorithms being implemented. And of course, in reality, any real solution is going to be a hybrid of this. It's going to have some amount of custom ASIC path for those things you don't think are going to change. It's going to have some amount of CPUs. It's got some amount potentially of embedded FPGAs to provide overall a solution for the SmartNIC. And we have to have memory behind that. So we're going to have on-chip memory, potentially in-package memory like HBM, or high-speed external memory like GDDR, or high-capacity external memory like DDR. And so if you look at requirements, some combination of these are going to be needed for these solutions. And one of the reasons I want to kind of look at all these differences here is because, as I said, different people have different requirements and are going to want a different mix of these for their SmartNIC solution for their data centers. So we've been looking at sort of what would be a good proof of concept for ODSA. And we think, as I said, there's a number of reasons why we think SmartNIC's a good candidate. And one of the things it does is it forces us to think about how does this perform as you start splitting functionality, as you start adding these interfaces into the design. So here is one possible configuration of how one could construct a SmartNIC out of building blocks of a network flow processor that's going to be your switch fabric. You can have a CPU for control plane. That could be something like a RISC-V core. There are other alternatives. I think one of the reasons we're here today is if people jump up and say, I want mine in there, let's champion that. I'm hoping we can get some, we'd like to have a bidding war here. Who wants to be part of this? FPGAs. FPGAs are a good way to do a generic domain acceleration. So for data plane acceleration, we're looking at what FPGAs. We're looking at using one of the older Achronix parts potentially in that role. And then then we need a bridge to connect to the Ethernet physical connection. The goal here is not to make a product. This would not be a competitive product in the market, but it would be a contemporary part. It would have performance that would be realistic enough that you could look at the software stack, you could look at the performance bottlenecks in it, and you could use it as a vehicle to assess, is a modular design like this practical? What are the challenges it presents? And I think that's one of the things we want to get from this audience is this a thing that if this was to be built, would programming this, would doing test deployments of this be a interesting step, learning step that is worth the effort of us undertaking? And if people don't think so, this is your chance to sort of help guide us to maybe do something better if this is not the right decision. Let me talk a little bit about, so taking this and kind of walking through what would be the main data flow through this. For your packet inspection and processing, the common case, you want to minimize how many steps you're doing. So you'd want to have it come in from the Ethernet or from the host, have a quick inspection, and hopefully in the common case that moves right through. Of course, we do want to have the data plane acceleration. So for those tasks, say encryption and decryption with new algorithms, we'd have the FPGA there that you could map to flow data. Now this immediately shows you, one of the challenges of a architecture like this is that you're moving bits now between chiplets, and if we don't, those could become memory bandwidth challenges. If you have sort of an exceptional case that your common data path can't handle, in most cases the NFP, network flow processor, could handle that and make the correct processing, but we would have to have an escalation path. So the CPU is there for the control plane, and so the escalation path is if the network flow processor cannot resolve the correct action, escalates to the CPU, which would then escalate to the host for further information. And of course, there would be the reverse of this as that new rules come in, how to populate those and map those in. Questions? Everyone's really quiet. So everyone's on board with this? Okay. You could take this and extend it. So stuff like adding storage and making a combined SmartNIC and Smart NVMe storage solution, so we can connect storage off of the data plane of this design. And so this would be sort of a next level of how to take this modular design and show how it can be even extended further. Of course, we couldn't even agree. So I showed you one design, and even amongst ourselves, we couldn't agree this was the right data path. So I guess you guys all failed because no one raised any concerns. So you could take the exact same components and you could connect them slightly differently and have a different data path. And so this is an alternative, which is to take the same building blocks. Instead of connecting the Ethernet straight to the NFP, you connect it straight to the FPGA. Now, there's a number of cases why this would actually be a more efficient data path through the NIC, for depending on what your workload looks like. So in this case, we would put into the FPGA the lookup tables, the matching tables for the common case. And one of the real benefits of this now is that for any sort of data-intensive acceleration, we have that now in line. So if we're doing encryption, decryption, or doing some sort of other acceleration or processing of that packet that required the data path of the FPGA now, that doesn't have to cross more chip boundaries. But the FPGA now, in the case of a exceptional case that doesn't match in our fast path, then you're going and having to do potentially extra crossings for the processing. And again, the escalation path would be the same, escalating to the CPU and then up to the host. So this just shows that even if you have the same chiplets, you can actually wire them differently and have a very differently optimized data path depending on what your sort of defining characteristics of your workload is or what you want to build with the system. So before I move on, I'd like just, I guess, on this, what do people think? Is this an interesting, my first question, is this something that was compelling enough if it was built as a vehicle for proving the concept? Is this interesting? Raise of hands. Who thinks it's interesting? Okay, who are the opponents? Who says this is not an interesting thing? So that's an excellent question. What are we competing against? So we have solutions out there. I think something that looks, let's just kind of take a step back here. Where are we today? SmartNICs are mostly in that 10 to 50 gig Ethernet space. We're seeing that on the roadmap. People are pushing 100, 200 gig Ethernet. We know 400 gig is on the roadmap of everyone. Let's take all the way a step back here. We have PCIe. You have to have enough bandwidth to your host to complement that. So today you're seeing sort of by 8 PCIe Gen 3 will handle something up to through about a 50 gig Ethernet. As you go beyond that, you have to go to wider and faster PCIe. So we have PCIe Gen 4 coming very soon here, which will double the PCIe bandwidth. And with 16, that'll take you to 200 gig with a PCIe Gen 4 system. Today we have solutions in the SmartNIC case, which are, some people are trying to do all custom ASICs. Some people are doing FPGAs. some people doing many cores. So we have all those in the market today. As I said, I think today the bulk of that's that sort of 40 to 50 gig Ethernet performance. We're not trying to say that we are fundamentally better than any of those. We're trying to say we believe this is a more flexible solution, that because each vendor, and I think if you ask Facebook or Google or Microsoft or Huawei or anyone else what they need in their data center, they all have a list of requirements, and there's a lot of commonality, but all of them have something different, which is why they're all partnering or building their own solutions now, because for their workloads and for their system architecture, they have slightly different requirements and they want different features.